may or by the late statistician slash other thing, Leo Breiman or Bremen. It's called Statistical Modeling the Two Cultures. So he was a statistician, like a theoretical statistician at Berkeley, and then he went to industry, and then he came back to academia, and his views changed a little bit once he did some sort of real data analysis. And at the time he was writing it, like the statistician, like these like the statistics community and CS community, let's say, they collaborated, but like at that point, still there was a little bit of divide, not complete, but there were people that were aware of the two cultures that he's talking about. But if you read, he's saying that there are basically two ways of viewing statistical modeling, or if you want, machine learning. So you can think of as, so statistics, let's say, starts with data. So everyone probably knows that. Machine learning also sort of starts with data. And you can think of data as being generated by some sort of mechanism. And the statisticians are like, okay, this is like applies in both cases. You can think of as there are a bunch of input vectors that go into a black box, let's say nature, and they output something. And then you get to observe why, and actually not necessarily observe why, but this is sort of something goes in, nature produces why. And sort of there is a prediction task, let's say. I want to, if I see X, I want to know what nature produces for Y. Okay, so that's one simple way of viewing sort of the statistics gain from a prediction perspective. So I have some variable, some input X, let's say. Let's say you have a sentence. This guy is like human. This sentence goes, the response comes out. So the response, like the ChatGPT example, we had it. So this would be the response to the question. So this would be a question. This would be the response that a typical human produces, let's say. So given the question, you want to predict the response. There could be like a range of responses, but there's like a feasible range of responses. You know that if you ask a question from someone, like what is a dog, there is a range of answers. And there is a range which is like, they don't produce a gibberish, like kind of like a random sequence of digits or a random sequence of numbers. Those won't occur. So this could be very general. So you could, I'm going to give you examples later. And then statisticians would traditionally try to model this box very carefully. Okay, so these X's, called covariates, so predictors, features, they go into like a very well-specified model, like a linear regression or like logistic regression, cost proportional model. And then there's the output, and then try to estimate the parameters so that this model is fit to the data, so you know the model. And then based on the model, you try to do various sort of analysis. So for example, whether this particular vector is like significant, like this particular covariate is significant or not, whether like the two like groups have the same sort of response or not. So people are probably familiar with this, okay? So especially if you're taking linear models or traditional statistics. So at the time, he estimated that 98% of all statisticians are like belong to this culture. So they try to model. There is like a well-defined model, and that's what they're doing. There's a bit of model evaluation, trying to see whether this model actually fits the data, but not as much. They do, for example, if you've seen regression in 1C, you look at the residuals, see if the residuals behave the way you want, if the assumptions of the model are valid, or so on and so forth. There's this algorithmic modeling which we got introduced to from the CS side, which approaches the problem a little bit differently. What they do, and he sort of advocates for doing it, is that you don't care what this inside is. So it's unknown and we don't necessarily care. We sort of bypass it, try to predict this our own way. And then it doesn't have to be exactly like this, as long as I can mimic what this is doing. So I don't need to like know how human functions, for example, exactly how the brain works or like what exactly is going on. As long as I can produce Y faithfully, like reasonably well, even if this has nothing to do with this, I'm fine. Okay, and then a lot of like complicated models, we can still call it models, but it's talking about functions. So there's an X function, f of X that you construct, and then this predicts Y or produces like a response Y. And this part could also be algorithmic. You can not worry about like just algorithmically produce a prediction, even if you don't understand the model well. So there is no way to write it mathematically, let's say, but you have like written a program, X goes in, prediction of Y comes out. And so he estimated 2% of statisticians belong to this field. And in this paper, he's trying to argue that you should more people should think like this. And I'm gonna maybe at some point point out some of the differences. But the main idea here, it's a little bit might be hard if you read it to get this point, unless you have seen a lot of statistics. But I encourage you to read it. It's very readable. He talks about his personal experience in the industry and what sort of pushed him towards this, and then the responses by statisticians, either agreeing with him or disagreeing with him strongly at the end. Like there's a like it was a controversial paper, but it's a very good paper. So this guy Leo Brayman is responsible for like the thing called random forest. So if you, how many people know random forest? Okay, so it's like a well-known machine learning algorithm, and he's the guy who proposed it and to advocate it for sort of the idea of bagging, which we may see, which we should use in decision tree. So decision tree is neural nets, let's say deep learning, so it belongs to this sort of class. The distinction is not very clear. Once we go into this a little bit, you might see that it might not be clear, but there is a clear sort of distinction. Hopefully at some point you figure out. The main focus here I want to take today is that the task is prediction. So you focus on the task of prediction. You're not going to focus on the model. Although there is an area, so let's now move on to my sort of bullet points. So what is basically, if you want to answer what is the difference between the statistics and ML, it's hard to separate them. So there's some sort of points in which more like CS type machine learning people focus on, and there are things that traditional statisticians focus on. The proportions of the two cultures are different now in statistics. So more statisticians identify with the CS type ML as well. But the focus, let's say that in ML, the focus is mostly on prediction, okay, not on inferring the parameters of a particular model. So you care about the prediction, and this makes the problem a lot more well-defined. So there's a clear answer whether you predict or not. Okay, it's very and it's very easy to evaluate. And then you don't often care about the being accurate models of the reality. As long as you predict well, you're good. At the end of the day, you might, once you have a good prediction, you might try to see whether this is a good, whether I can simplify the model, whether I can make the model more interpretable. So black box models are often like they're like the staple of ML. So in the ML case, for example, the thing that achieved the performance of ChatGPT, it's not in the model that you can write down like a linear regression model, or you can sort of handle it's like billions of parameters, like I don't know, 173 and something like. It's a model with that many parameters. It's not like 2 or 3 parameters. So it's not a model that you can easily handle. It might not even fit in your like the laptop memory if you actually so there are tendencies in ML nowadays to look for interpretable models. So classical statistics care about interpretation. I want to interpret the model. So once I fit the model, I can like see what each sort of predictor is doing and so on. There is a like subset of ML people that care about this now. But traditionally, let's say if you focus on the prediction task at first, you may forego this for a while. You may say, let's see what we can do. What is the best we can do later? We'll worry about interpretation. Okay, that's one of the distinctions that you see. The line nowadays is somewhat blurred, as I mentioned. So more people from the ML side realize the importance of interpretation, especially if you make a prediction in a sensitive field. You want to see what the basis of prediction is. If you're going to decide the sentence of someone who's done a crime, if the AI turns out to try to do that, you want to make sure you know what the basis of that decision is. If it's or in healthcare, if you want to make it a medical decision, you want to know what are the reasoning going on. So it's not just predicting. I know 90% of the time you predict well. You want to know in this particular case, what is the basis of the prediction? Maybe the doctor wants to evaluate it. So there are areas in healthcare, in cases where there's high risk for decision making, especially large scale systems. There's value in these. But at this point, the people that push things like ChatGPT and things like this, they set aside the idea of interpretation and said, what can we do? How can we achieve the best possible prediction? The best predictive performance. Let's say I have a human in the middle. I'm going to predict what a human does in different situations. Right? If I can predict it very well, it's going to be indistinguishable from a human. So that's the kind of AI that we hope to achieve. So that's what I'm going to do here. I'm going to, in this course, focus on the prediction problem. And so that would shape some of the things that we talk about. So, and specifically ask if you have taken 100C, this is also very useful. But because we talk a lot about the interpretable model in other courses, especially 100C and other courses, I'm gonna in this course, I'm gonna focus on the prediction problem. You can see what we can do in terms of the prediction. And the last thing is that we're gonna look at it from a probabilistic perspective. That's not the only way that we can view the problem, but we're gonna assume that there is some randomness uncertainty in this mechanism that's generating the Y. So this is not a deterministic mapping. You can imagine if I ask a question, even if I ask you a question, you might have different responses depending on which time of day I ask you, or what are the context of the context could be part of X. But there is variation. There is some variability, and that's where statistics shines. So whenever there's variability or uncertainty, probability and statistics really can help. So we're going to focus on probabilistic prediction. That's basically my introduction to the field. We're going to start very simply. So don't worry, we're not going to start from ChatGPT. Okay, so but it would have been a nice demo. Any questions? Still down. So questions, comments? Does this make sense to people? Okay. So a little bit more formally, what we're going to, for a while, focus on is this idea of, let's say, a prediction problem you can think of as we observe a feature X belonging to some script X, and then we want to predict some outcome Y based on it. And of course, there should be some relation between X and Y, and we get to how we model that. But here are some examples from Peter Broadwell's slides on a different course. So X could be a document, and then the Y could be the topic of the document. So I give you a document, you have to determine what the topic is. I give you the image of the handwritten digit, you have to know what the digit is, predict what the digit is. Image of an object, the type of the object would be what I want to predict. Image of a signature, the identity of the writer, this might be a little bit more challenging. Email, for example, whether it's spam or not. A sentence, let's say parse tree or something else. Medical test, you want to determine the disease type. Gene expressions, for example, whether it's cancerous or not, these are binary decisions, for example, and so on. Okay. But for example, web search query, that would be a ranked list of pages. In the ChatGPT case, for example, a question and then an answer. Okay, for example. Okay, it could be very variable. So you can say even modeling X here would be a little bit tricky. Okay, the X could be discrete. So for example, how do I model a document? And then images are a little bit easier to, image could be like a 2D matrix, but you can see it's not necessarily in the traditional sense. A lot of the NLP, like natural language processing or applications, deal with text, and then you have to model text. So the input is text, but the output could be usually the output for us, we'll see. We start from very simple output. We start from these binary cases. Okay. Good. So I'm going to start from this running example. There's this data set, which is rather simple. What we have here is like the passengers of the Titanic, the ship that sank like roughly 100 years ago or more. And then there's some statistics or some information. So the data is like this matrix. I'm assuming that people are familiar with data. So like what we usually in these cases have is not just a single X and Y, but we observe multiple cases. Okay, so here we have multiple passengers, and then this column, whether they survive or not once the ship went down, that is encoded as 0 and 1. So 0 is they survive, 1 is they survive. This is their sex, like male or female, passenger class, the age, and there are a couple other like covariates or features. So these are the features, and let's say I want to predict this, whether they survive or not. Okay, so this is a very simple problem, but we're going to stick with this because this is gonna you can sort of flesh out a lot of the issues here. So let's say for now I'm going to pick this as the Y. I have a random variable Y that takes value 0 or 1, whether a passenger survives or not. And the covariate, let's say I take 6 as the covariate, whether they're female or male. Okay, I just have this information. This is binary, this is also binary. I just know whether they're female or male. And I want to predict whether they survive or not. This seems to be simple, but I want to point out that even this simple problem, you see some interesting phenomena. Does that make sense? Later on, I can sort of incorporate, for example, this column as well. So I can take, for example, these 3 columns. This is still a discrete value, so it's like 1, 2, 3. So there are 2 classes, but this is like a continuous variable, the age, right? So this is a binary covariate. This is like covariate with 3 states, and this is like continuous covariate. So features could come in different formats, right? But I'm going to focus on this. And I'm also going to focus on this case where things are binary. There's this informal distinction between the ML people and stat people. If you open a book, if it starts with linear regression, the author is usually a statistician. If you open it starts with classification, it's usually an ML person. It's not a formal distinction, but it's a very good kind of, you can train a classifier to classify whether the person has a stat background or ML background based on whether you start from classification or regression. So this problem that I'm looking at, because the line is binary, this is called a binary classification problem. I just want to classify each passenger into one of the groups. Okay, and we're going to start with this to sort of pretend that I am a machine learning person. Although we're in the stat department, but because you have also seen a lot of regression, linear regression, you're going to start with this. Hopefully you learn a little bit more. Good questions, comments. Okay, so the part that I'm going to go over, so this is data, this is real data, let's say. But what I'm going to go over is first assume we don't have any data. And I want to see whether what can I do? So before doing that, so let's say the goal here is to predict Y for a given passenger. based on the value of x. So what I'm going to do is I'm going to learn. This is the machine learning part. So I'm going to learn a classifier. What do you mean by learning classifier? I'm going to basically learn a function. So I want a function that maps x to a number between not between either 0 or 1, which I'm going to call y hat. And so this is going to be approximately what y is. So for example, if I give you x, in this case, female, male, you output either 0 or 1. So this is a very simple function. It takes two possible values and outputs two possible values. In general, if this is more complicated, it's still not going to output 0 or 1 because it's binary classification. So for binary classification, this would be, for now, it's going to be either 0 or 1, but the input could be different. So that's what I'm going to do. I'm going to learn this function. And what I'm going to do is I'm going to model the relation between x and y as the probabilistic model. That's the probabilistic part. So I'm going to assume that this pair of random variables comes from a joint distribution. Okay, so there is a distribution on x cross y, and this notation is this is distributed according to that. So at this point, it's abstract, but we're going to like talk a little bit about it. So the main point is that I don't know generally this distribution. Okay, so I just get to observe samples of copies of this from this distribution IID, but I don't know the actual distribution. And that's the difficulty of probabilistic prediction. So we don't know the underlying distribution, we just get to observe copies, as we'll see in practice. So this, for example, table gives you copies like x1, y1, that's one passenger, x2, y2, x3, y3. Here, each row would provide, so this would be x1, this would be y1, this would be x1, this would be y2, x2. So the data comes in like that. So I get to observe samples, which we assume that they're IID from P, but we don't get to observe P. Okay, that's the setting. For a while, I'm going to actually pretend that I know P. Okay, that's what I'm going to do. Assume that I know P and see what is the best that we can do. Okay. For that, we throw away the data. Let's say I throw away the data. I want to specify what this P is. I'm going to give you the P. So someone like an oracle knows this P and it gives you. So the first question is, how do I specify this? If I want to give you the P, how should I specify it? In this simple case where I have X belongs to, it has two levels, like female, male, and then Y is 0, 1. I have a binary variable X, binary variable Y. How do I specify joint distribution of X and Y if I want to give you the P? Okay, great. Get 2 by 2 grid. So that would be all the information I need. So let's say 0, 1, this is X, this is Y. And this would be probability, for example. This would be probability that X is equal to F and Y is equal to 0. Right? This would be the probability. Let me do this. This would be the probability that X is equal to M, Y is equal to 1, and so on. Okay. Sounds good. So a bunch of numbers, 4 numbers. If I give you, I specify fully this joint distribution. Everyone on board with this? So for example, I can give you this. This is the table that we have. There are 4 numbers. This is, for example, the probability that X is equal to F, Y is equal to 0. This is the probability that X is equal to M. Y is equal to 0. So this is just a test to see if people remember probability. This is okay with everyone? But this is a full specification of the joint distribution. So some of the what are the properties of these numbers? Can I put any numbers here? Should they satisfy constraints? Can they be negative? No, they're probabilities, so they have to be positive. Can they be bigger than 1? No. What did you say? all of them, they have to add up to 1. Okay, that's the big concept. It's like all of them have to be negative, and the sum, they have to sum to 1. Otherwise, you can have any combination of the numbers. Right? Again, as a warm-up, from this we can compute the marginal distribution of any one of these variables. So this is x, this is y. So what is a marginal distribution? Anyone knows what I mean by the marginal distribution of y? Okay, that wasn't. Anyone? What I mean is, like, what is the probability that y takes the value 0 and the probability that y takes value 1? This is the marginal probability. How do you calculate this? Yeah. Yeah, so I sum this column, right? So that basically the row sum or column sum give you the marginals of marginal distribution. So this is going to be 0.62. It's going to be 0.38, something like that. Right? And then you can calculate the marginal distribution of x as well. That actually would be like n. You can do that. Okay, so far so good, right? So now the question is, now I want to learn the function. So I give you x, let's say. I want to predict y. So first, I want you to think about the simplest possible classifier. So these things are called classifier. So the things that classifier is this function that maps x to 0 or 1. Okay. Here we have binary classifier. What is the simplest one is basically the one that ignores any polarity. So let's say I want to ignore x. How do you like predict y? I want a classifier that doesn't care about, let's say, sex. I give you the sex, but you're not going to use this. Yeah. Okay, so you're going to use the marginal distribution of y, and then pick the one that's sort of bigger, right? And so you're going to guess that. So the classifier would be like, I'm going to call it F1. This is our first classifier. Takes x, and it just always outputs 1, right? No matter what. Sorry, outputs 0, no matter what the value of x is. So basically, f of x is going to be 0 if x is equal to f. 0 if x is equal to f. Okay. Does this make sense? Is it reasonable? So what this is saying is that roughly, like, if you look at the population level, 62% of the people die, regardless of any other covariates, and 38% live. So if you want to ignore everything, your best guess is probably that if I give you someone, it's more likely that they not survive. So you're gonna assign that. So this is a constant classifier and sometimes called the majority rule. So this is a baseline you can always use to check what you're doing. And surprisingly, you can fit a very complicated model, and sometimes you can beat this. So there are people who have written papers, they have like tried to predict, let's say, particular case of interest of mine is that there's a line of work by someone who tried to predict divorces. So whether marriage ends in divorce or not. And they say, oh, we have figured out like we can predict with 80% accuracy, or like 87% accuracy whether marriage fails or not. And you look at the data, and if you do this, you beat that statistic because most marriages don't fail. Let's at that data set, let's say you can predict that it would not fail, right? And then you beat this. So it's a good baseline, and but we can do better. So now, is this fine? Just remember this: every time you do classification, always do the majority rule classifier. Okay, let's say if I give you a binary classification task, and you data like a very, like a 100 billion parameter neural network, and you get a result, you can always check against this. If you can't beat this, then it's not useful. We're going to talk about what we mean by beat. So how do we measure performance? But this is called the majority rule classifier, and it's your first guess. Okay. Now I want to add the feature. I actually want to use the X. So what should I do? Can I do better than this? Can you guess how to do it? Yes. Joint probability is this guy. But you have to output a classifier. That's what you have to output is, you have to tell me, this is actually, let me put this here. So that's the majority rule classifier. So if you can, let's say if you want to be a little bit mathematical, F1x is arg max probability that y is equal to, I'm going to say D. Let me do this first so that you're a little bit familiar with the notation. Sorry, not D. Yeah, B is the decision one. So what this is saying is that I'm going to look at this as a function of D. For D equals 0 or 1, and argmax is, I'm going to pick the argument that maximizes this. Okay, I'm going to plug 0 here or 1 here, and then choose the decision that. So I'm not going to choose the value here. So the value that maximizes, the maximum is 0.62. The value that maximizes is 0. That's the argmax. Okay, so the majority rule classifier, you can write it like this. In this case, you can see this has nothing to do with X. So if I vary X, this sign is not going to change. So it's going to be constant. And so that's like mathematical way of writing. Is that, yeah?
No, so would you use the conditional probability?
Okay, good. Yeah. So now I wanna do like a classifier. So you have to tell me what are these two, like under female or male, what should I predict? If I predict 0, 0, I'm back to the first case. But you have to tell me, like, there are other choices. Like I have 1, 0, 0, 1, 1, 1. These are other possibilities. So now conditional probability. So what exactly do we do?
Like if we know that X is a female, I guess we'd say P Y equals D given X equals F.
Good. So we're going to look at probability of Y equal D given X is equal to female. And I'm going to also look at the probability of Y is equal to D given X is equal to male. Okay. And do I have to consider both 0 and 1 here, or the is it good to just consider 1 here, or should I also consider 0 as well? There are two possibilities for Y, right? So if I compute probability of Y equal 1 given, let's say if I compute this, do I sort of get probability of Y equals 0 given that as well? Right. Yeah, so it's going to be 1 minus that. So basically, it's just enough to, in the binary classification case, sort of, it's almost enough to just look at one of the outcomes. And because I care about the survival, I'm going to look at probability of Y. So under whether X is female or male, I'm going to look at the probability. So how do we calculate these probabilities? Let's see how many people remember basic probability. Yeah.
Oh yeah, if the Y equals 1 and X equals F over Q equals 1.
Over, sorry, what?
Or over
P equal 1, Y?
Yeah.
Do you say this? Is this valid?
Or no, P equals F.
Yeah, there are two choices. Which one it is? Say, is this the one or the other? So what you said is the other probability, right? So this is the probability. Like the joint probability of this divided by the marginal probability of this side. That's sort of the basic idea of conditional probability, right? Just a reminder what it is. So if this, hopefully everyone knows this, right? So I can calculate this based on the value in this table. Let's do it here. Yeah. I'm gonna write this here. 0.1, 0.26. Memory is not good. 0.52, 0.12. Yeah. So what is this then? Point 26, yeah. So what is the probability of X? Sorry, 36. Yeah, so that would be the sum of this row, yeah, 36. Anyone has a calculator? So what is this? Sorry, what is it? 0.72. Okay. Okay, good. Looks correct. So this one would be probability y equal 1, x equal m, divided by probability of x equal m. What would this be? Y 1 m, right? That's 0.12. What is the probability of x being male? .64. So someone calculates this. Please. Sorry. 18. Okay, so I have 19 here probably if you round it. Maybe 19. Sort of 18 is good. Oh, actually 18, right? Why did I? 19 is not good because they don't add up. Oh, actually, no. Let me do 19. Do they have to add up? Should these two numbers add up? No, 19 is fine. Okay. It might be around there, but it doesn't matter for our case. So what is the conclusion? So we did these calculations. So what is your classifier now? So for example, let's say f(x) is f. Another probability that y is equal to 1 is this. You can also calculate the probability that y is equal to 0, right? So it is the probability that y is equal to 0 given x is equal to f. Sorry?
Oh, 0.18.
0.18, yes. Same goes here. Y equals 0. That would be, what would it be? Yeah. Say 0.71. Okay. So what is the conclusion?
0.28.
81, yes, okay. 81, 28. Good. Good. So what is the conclusion now? What should our classifier be? 1 if it's female. Yes. Right. Why? Based on, sorry? Majority. Okay, good. Yeah. So which one of these probabilities is higher? So I want to decide. So conditioning is like once I know, you probably usually condition. So condition on the known information, which is let's say X is female. Given this now probabilities change, Now the marginal probability was that it's more likely to not survive. But given that you're a female, the conditional probability now is higher that you survive. So 70.5 versus 0.28. So you guess this one, the one that's higher. For if you're a male, it's like less likely, right? It's less likely that you survive. So it's 81% that you not survive. So that would be, in this case, it's more likely to be 0. So in the case of the x equal to being a male, the decision is not changed, but in the case of a female, it will change. Okay, so this is a different decision rule. So the original one was this. The majority of this is like that. Does that make sense? So this is sort of intuitive if you understand conditional probability, right? So now the question is that, is this really a better classifier? So how do I know that you have the idea that, yeah, conditioning, you should condition, and you pointed this out, it's actually a good classifier, but can I first, let's say, do better? Or whether this is gonna beat, is it actually beating this majority rule? How do I know that it's better than majority rule? Maybe you want to think a little bit about these two questions. Let's say, how can I show that, for example, first, I don't know, but let's say you guess that this is a better classifier because it uses more information. The first one ignores the covariate. This one uses the more information. What is it that we should, or we can do to try to convince someone that this is a better classifier? Yeah. Accuracy, cross-validation, these are good ideas. So we want sort of, let's say, a measure of performance. Accuracy is one measure of performance. So in order to compare two classifiers, you have to have a measure of performance. Okay, so you have to agree on a measure of performance, and this is debatable, which measure you choose. But once I choose a measure, then I can say this one is better than that. Before that, there's no clear answer. So we need some sort of a measure of performance. What we're going to do, which is fairly general, is that we pick a measure of loss. Okay, so what we have here is like the true label. This is the estimated label. So y hat is f of x, let's say. And I'm going to pay a loss, which is fairly general at this point. We're going to specify one particular loss function. Once I have this is going to be random because both x and y are random. So y hat and y are going to be random. So it's a random variable. And people, what they do is they take the expectation, which is called the risk. So the expected loss is called the risk. If I want to like write it, it would be like that. If I plug in y hat, it would be like this. So I know the joint distribution of x and y. I know what f is, then I can compute this loss. So this is fairly general. The particular loss that we start with, and it's very common in classification, uses the loss which looks like this. So this notation is the shorthand. It's called an indicator notation, which is useful for you to know. What it's saying is whatever is inside, if it's true, the value would be 1. If it's not true, the value would be 0. So this is saying if basically it's like a shorthand for this would be 1 if y hat is not equal to y, and 0 if y hat is, sorry, the other way around. Y hat is not equal to y, and y hat is equal to y, right? So if whatever is inside is true, then it's 1, otherwise it's 0. Okay, so this makes sense if y hat is equal to y, I'm correct, so I don't want to pay any price. If not, I'm going to pay a price of 1. Okay, that's the idea. And then I take the expectation, and that in that case, the risk is called, so for this, the risk is called accuracy. It's like the on average, on expectation, how will you do? So So in this case, there is another formula. If I write the expectation here, the expectation of the loss would simplify. There's a simpler formula for it. Anyone knows an alternative formula? What is the expectation of a binary variable or an indicator variable? So the risk here is the expectation of 1. So this is a random variable because y hat and y are both random variables, either 0 or 1. What is the expectation of a random variable that takes value 0 or 1? Anyone remembers? I flip a coin, right? Probability p comes up with 1, probability 1 minus p comes up 0. What is the expectation of this random variable? Not have p, right?
Oh, yeah.
But probably p comes up 1, probably 1 minus p comes up 0. The expectation would be p. Why? How do you calculate the expectation? Right. So if I have random, like a variable which takes 1 with probability p, 0 with probability 1 minus p, the expectation would be 1 times p plus 0 times 1 minus p would be p. Okay. So now this is a random variable, takes value 1 with some probability, takes value 0 with 1 minus that probability. So that probability we can just write as probability of y hat equal y. So this takes value 1 with probability, this event takes value 0 with 1 minus that. So the expected value of a 0, 1 loss is just the probability. So that's another way of writing it. This is accuracy. It tells you what the probability is of you disagreeing, like your classifier disagreeing with the truth. Okay, but this step, if it's not clear, think a little bit about this for yourself. So it's just a binary variable, takes some value with probability p, which is this, and 1 minus probability, probably 1 minus this takes value 0, but that doesn't count here. It just gets vanished. So this is called accuracy. So this is a fairly good measure. Not always, but for now it's good. Like this is the natural. You can see this is not. This is natural. So this is saying. So if you understand what we did, this is a random variable. This is also going to be a random variable. This tells you on average, what is the probability that you disagree? It's going to be something between 0 and 1. If the probability is very small, this is a good classifier. If the probability is close to 1, it's like most of the time you disagree, which is not good. But depending on the value, this is a good measure, sort of intuitive. Is that clear? Right. Here. So let's try to compute the accuracy for the 2 classifiers that we had. Right. So I have 2 classifiers. We can use accuracy for F1 versus F2. So F1 just outputs 0 for both values of the covariance. So how do I calculate the probability? So this would be my y hat here. Let's say y hat 1 if you want. I want to compute probability y hat 1 not equal to y, which is the probability of F1x not equal to y. So how do we proceed here? I'm just going to plug this in because it's always going to be 0. So this is the probability that 0 is not equal to y. I can do that because it doesn't matter what value of x we have. So what is this? Y takes 2 values, right? 0 or 1. This is going to be probably that y is equal to 1, which is, you have to go back, if you have your notes, 0.38, right? So pick the big one. You can see if we pick the other decision, this would be flipped. So we pick the one that was bigger, the probability was bigger. So here we get the smaller one. So 0.38 is the accuracy of this. 38% of the time you make the error, which is reasonable. So 68% of the time you're correct, 30% you're incorrect. So that's your accuracy. Okay. So that's the accuracy of the baseline majority rule classifier. So it's a baseline. It's always good to calculate this for yourself if you're doing binary classification. So the data is, you can see it's sort of what they call imbalanced, a little bit imbalanced. So it's not like 50-50%. If probability y equal 1 is close to 50.50, this is not very useful. But if two classes have very different probabilities, this is not a bad rule. So at least like you're doing better than a coin flip. So if you flip a coin, 50% of the time you're gonna be wrong. This is better than a coin flip. So how do you calculate the other one? So the other one is a little tricky. Y hat 2, let's say, is f2 of x. That's the other classifier, which is 1. If x is f, 0 if x is m. So I can start writing. So case 1, case 2, y hat 2 is equal to not equal to y. It's going to be probability that f2x is not equal to y. Okay, at this point I can't simplify easily because the value of this depends on x and x is random. So what do you suggest we do here? How can I account for x? Yes.
Guessing.
Okay, guess is good. Okay, conditional probabilities, 2 conditional probabilities times multiplied by. So can you tell me like what to write? We can condition on x. The way to do this is to condition on x, because once I condition on x, the value y hat 2 is completely determined, right? So what I can do is like I can say, whatever this is, conditional on x being, let's say f. There should be something here plus whatever. So let's say this is event A. So A, and then times something, event A conditional on x being m. And then I need something else here. I can just add the condition. There's something more here. Okay. The basic rule of like, I don't know what it's called, law of total probability, or like, how do you do this? If you want to break up based on the, yes. Yeah, I'm going to fill this part. I'm going to talk about this. What should I multiply here? Yes, okay, good. So that's x equal to f, x equal to m. Hopefully you remember that this is, so if you multiply, this is just basically joint probability. So now you were saying something, so what should I do here? Great, yes. 0, okay, good. So once I condition on x, the value of f2x is determined, in this case, under this assumption, this is going to be 1, and under the other assumption, it's going to be 0. That's how we define. And then I can say that this is the probability that y is equal to 0. You can see the decision that we make, the flip side is going to be the error. So we made the decision 1, and we're going to pay the price of y equal to 0 here, times the probability that x is equal to f plus the probability that y is equal to 1 given x is equal to m, times the probability that x is equal to m. Okay. So if you go back to your notes, so what is this? That's the flip here. That's the 0.28. and the other one is 0.19. So we picked this one because it was bigger, so we're going to pay the smaller one. So if you're not wrong, so this is going to be 0.28. This is going to be 0.19. And you should check. And then what is the probability that x is equal to m? So you have to calculate it here. X is equal to m is 0.64, right? F 0.36, right? So I get 0.64 here. So basically what this is saying is that for 64% of the population which are male, I'm going to make 90% of the time a mistake. And for 38% of the population which are female, 28% of the time I'm going to make a mistake. This makes very much sense. Okay. And so you calculate this, and you do the calculation almost all the time, but they're also done almost. So what is the value here? 0.22. Okay, I did like 0.58, but it could be 0.24. It's close. Did you do 0.24? Like, who did you calculate? Is this correct? Okay, maybe I did wrong, but it's like close, like 0.24, 25, 26. It's better than 38, definitely. Okay, so we put the measure of performance down, like accuracy, and you can definitely say that this is better. Okay, so your accuracy is better. So on average, overall, you can do better. So if you think about this accuracy as we're gonna get to this, but this is a like probabilistic statement. But what it's saying is that if you test many different passengers, so if you imagine a frequent interpretation of probability, if you give me 100 passengers and you give me the feature, like whether they're female or male, and I'm gonna guess based on this classifier and that classifier, on average, I'm gonna make this error because by the law of large number, the number of errors that I make converge to this, because we'll see that converge to the expectation. So 26% of the cases I'm gonna be wrong, in the other case I'm gonna be wrong on 38%. So this is a better classifier. Okay. So that's good for today. Next time we come back and we can think about whether you can do better. Is this the best we can do? Or can I make it go down further, given this information? That's what I'm going to do. Okay, thank you guys.
Thank you.